the X-ray diffractions. Okay. So X-ray diffraction. So I mean, before we were having the topic that was X-ray. Now here X-ray diffraction, which is known as XRD. This is different from the X-ray. Okay. Here we are just using the X-ray, but with the help of the X-ray, we do the diffractions. Okay. So this is this is completely different from the X-ray um, techniques. Okay. So here X-ray diffraction (XRD) is a non-destructive techniques method used to analyze the crystalline structures of the material. It helps identify the phase, crystal orientation, grain size, and residual stresses in the material. So what is the purpose for which where we are using the X-ray diffraction or XRD to analyze the phases, crystal structures, crystal orientations. Basically, in simple, what you can say, the crystal structure. To analyze the crystal structure. In crystal structure, then we could analyze also the phases, crystal orientation, grain size, residual stresses if any present inside the material. Okay. The key features determine the crystal structure and the phase compositions, identifies the defect, residual stresses, and texture in the material used for the quality control and material characterizations. Okay. So what are the principle of the X-ray diffractions? The X-ray diffraction, the X-ray is based on the law which is known as the Bragg's law. On which law the X-ray XRD is working, which is known as the Bragg's law. Okay, which state that the X-ray diffracts when they interact with the atomic planes of a crystalline materials. This is the statement. Okay, how it works? A monochromatic X-ray beam is directed to the sample. I mean, we must have to induce a X-ray first. Okay, that will be focusing, that will be incidentating over the material. The X-ray interacts with the crystalline lattice and are scattered. When once it gets inside the material, then it gets scattered. Okay, okay. When it is scattered, the waves satisfying the Bragg's law, okay, they interface the constructive products producing other different patterns. Okay, the angles and the intensity of these diffraction peaks are recorded and analyzed to determine the crystal structure and compositions. What is the Bragg's law? Bragg's law formula is like this: n lambda is equal to 2d sine theta. N lambda is equal to 2d sine theta. Where what is the n? N is just the integer. It could be anything. It is just a number. Okay, lambda is the X-ray wavelength. Wavelength and frequency. So here what we are taking, lambda is just a wavelength. Okay, wavelength what? Wavelength. If you have like this kind of the wave. Okay, so if we just peak to peak distance is known as wavelength, and if we talk about the value to value, then it is also the wavelength. That would be the same. This is known as the wavelength. Okay, so here lambda is wavelength, d is the interplanar spacing. So interplanar means if you have the plane like this, one plane, two plane, three plane inside the material. So in between these two plane, what is the distance that is known as d inside the material? It is just about the material. Okay, if we talk about the theta is a diffraction angle. I mean, if they are coming inside, I mean, this X-ray is coming and it is going like that. Okay, so what is the diffraction angle? This angle is known as how they have diffracted. That is known as theta. Okay, with the help of this, that we can find out easily, the value of, uh, uh, this is basically the, if anything, suppose, most of the time what we do, that we are requiring this d value. We must, because lambda is known, n is known, sin theta is known, or sometimes we have known about the d, but we need to know the theta. But what mostly we need to know the d. Once we have decided the d, or we are able to calculate the d value, then we can basically in a position to explain what kind of the structure structure is there inside the material. Okay, so key components of the XRD: the X-ray sources that produces the X-rays, I mean, we must have the X-ray source so that we can induce the X-ray. Sample holder, the material must be holding, must be kept over the holder so that it can placed in a right position where X-ray can incident. Okay. Goniometers, rotates the sample and detector at the precise angle, right? I mean exact angle. Detectors record the diffraction patterns at recorders. Types of the different XRDs methods. First one is the powder XRDs, single crystal XRD, thin film XRD, and residual analysis XRD. These all are the just the methods. Okay, and for what the methods diffraction from the randomly orientation border sample. These all are just a different techniques. You just need to know what are the different kind of different XRDs present. Okay, important is what are the steps. Okay, first one is the simple preparation. The powder samples should be finely ground and evenly spread over the material. Bulk materials must have a flat and polished surface. Second step is setting up the XRD instrument so that they select the appropriate X-ray sources where we can generate the X-ray. Okay, calibrate the goniometer for a precise angle measurement. Third one is the X-ray exposure and the data collections. The sample is rotated and X-ray diffraction data is collected. The detector recorded the diffraction angle 2 theta. Okay, so here what we have shown you this angle was basically 2 theta, not only theta, basically the 2 theta. Okay, so data analysis and interpretation. So different peaks are compared to the standard database. Okay, the phase compositions and crystal structures stress state are identified. Report and material characterizations. That is very simple. We have already done what we have to do in the reporting and material characterization to measure the to compare with the industry standards. Okay, here interpretation of XRD patterns. Okay, so how we can interpret these are just causes. Sorry, application part that we are not concern here, but what is the interpretation if you are getting the high crystalline structures material, the sharp, intense peaks that we will be having in detector. Okay, amorphous or non-crystalline materials, then we are having the broad peaks. If we have the peak shifting, it means the lattice strain or residual stress is there. If we have an additional peak, it means the presence of the impurities phases. If we have the peak intensities variation, it means they refer to the crystalline orientation, mixed textures. So these all are just a interpretation of XRDs. Okay, what are the advantages of the XRDs? The advantages are just requires the minimum sample preparations. Okay, the precise phase identifications, even for the complex mixture. Determine the lattice parameters, strain and crystalline sizes. Application applicable to the various material like the metal, ceramics, polymers. Highly, you know, reproducible and reliable. Imitation only the works on the crystalline materials, not suitable for the amorphous material. So for the amorphous material, we cannot apply these techniques, XRD techniques. Okay. Requires a well-calibrated database for the phase identifications. Expensive equipment and specialized trainer is required. Here it is very costly. As you can see, as we are just moving bottom side inside the slides, their cost is increasing. They require more skill, more equipment and highly expensive equipment and more highly experienced person who can do that inspection. So as we move downward inside the slides, okay, whatever the technique that we have studied till now. Okay, so these all are just limitations. Okay, so what is application? Application, but the same kind of things. Just we're living here. Okay,